Okay, let's go ahead and get started working on some chapter 17 questions. In 17.8, we have the sweetening colas example that we were looking at in the slides. The p-value for the first cola in example 17.5 is the probability taking the null hypothesis mu equals 0 to be true, that X bar takes a value at least as large as 0.3. A, what is the sampling distribution of X bar when mu equals 0? The distribution appears in figure 17.2. That's included here. And then they ask us do a normal probability calculation to find the p-value. Your results should agree with the example 17.5 up to round off error. Okay, so they want us to look at this figure and say what the distribution is. It's a normal distribution. We know that by looking at it. It's a bell-shaped curve. So it is a normal distribution. The mean is mu, and the standard deviation is sigma divided by root n. So we need to find these values. We were told that mu was 0. And in the figure, we can see what sigma and n are. Sigma is 1, n is 10. We need the value sigma divided by root n, which is 1 over root 10. 1 over root 10 is 0.316. And now we can just write the distribution as the normal distribution with mean 0 and standard deviation 0.316. So that's our answer for A. Now, B asks us to find the probability to calculate the p-value. So the way we calculate the p-value is listed here. We picked this particular rule because the test has the greater than, and so we picked the rule associated with the greater than. This table is on the summary in chapter 17. Okay, so what else do we need? We need the test statistic, which is up in the corner. So Z is equal to X bar minus mu divided by the standard deviation of the sampling distribution, sigma over root n, which we found a value for. Now, the only other piece of info we don't have written down was given to us in, well, they say X bar that takes on a value as large as 0.3, but then also in the figure, we have X bar equal to 0.03. So X bar is 0.3. And now we can fill it out the z-score. 0.3, take away 0, divide by 0.316. This is a 0.3. divide by 0.316. That gives me a z-score of, well, first it gives me a value that I can then use to find the z-score because I have to round to the nearest two digits. Now we need to go to our table A here and find our 9, 5. So our z-score associated to the 9, 5 gives us an area of 0.8264. But the table gives us the area to the left of this mark. We need the area to the right. So I always call what I get from table A, and then we need this rightmost edge. So we're going to take the value away from 1. The 1 minus 0.8264 gives me the value of 0.1711. Now, p-value is, according to this, the probability that we would get a z-score more extreme than our z-score. We found that to be 1711. So our p-value is 0.1711. Okay, so checking our answer, we've got the normal distribution with mean 0 and standard deviation 0.316. They took it to 4 decimals. We left it at 3. And then they got the p-value of 0.1711. So check, check. Okay, in number 9, we have a similar situation. We were also looking at this example in the PowerPoint slides, the job satisfaction problem. And this one is a two-tail, which is different than the last one, because here we just don't think that mu is equal to 0, but we don't know if it's less than or greater than. So we have to consider both ends. And there was a typo in the slides, and I told you I would tell you about it. And so here's the corrected version from your actual ebook. Okay, so let's read the question number 9. The p-value in example 17.6 is the probability taking the null hypothesis mu equals 0 to be true that x bar takes a value at least as far from 0 as 17. So at least as far away from the mean as 17. What's the sampling distribution of x bar when mu equals 0? The distribution is shown in the figure 17.3. So we do have a normal distribution with mean mu and standard deviation sigma over root n. So we have to find our pieces, right? we have mu equals 0 in the first box. We have we have sigma equals 60. We have n equals 18. And we may as well grab it. We have our x bar equals 17. And I got all of this from the figure itself. Okay, now we might want to find sigma divided by root n, which is the standard deviation of the sampling distribution. So 60 divided by the square root of 18 gives me 14.142. So our distribution here is normal with a mean 0 and a standard deviation of 14.142. Okay, so part B wants us to do a normal probability calculation to find the p-value. Recall that the alternative hypothesis is two-sided. That's what the not equal to means. And your results should agree with example 17.6 up to round off error. Okay, so let's calculate a z-score and then use the table A to find values. And this time we have to consider that there's two n's. Okay, so let's start with the z-score, right? Z is equal to x bar minus our mu divided by the standard deviation, sigma over root n. This is 17, take away 0, divide by 14.142. So 17 divided by 14142 gives us a z-score of 1.20. And now we look at our table A. And we see that the information that the table gives us is up to that positive z-score, 120. So the table gives us an A of 0.8849. That means the area to the right of this mark is 1 minus A, which is 1 minus 0.8849, which is the value 1151. Okay, now they give us how to find our p-value here. And p-value in a two-tail is 2 times the probability that you get a z-score more extreme than R120, because more extreme than means that you're in the critical regions that are shaded blue. And if you're more extreme, but on the left side, that's just going to be negative z-scores instead of positive ones. But you have that same amount of area on the other blue shaded region. So the p-value is both of those areas together when it's a two-tail. Only when it's a two-tail. This gives me 0.2302 as a p-value. All right, so checking with the book, we get the normal curve of 0 at the mean and 14.1421 at the standard deviation. We also find we match the book 0.2302 on the p-value. Okay, so those two examples were presented in the PowerPoints and in the book. We've just sort of touched on them again. We haven't completely finished the conversation. As we'll see in other questions, they'll ask us what that p-value means and if that means something for our client. Okay, number 16, we're going to use the table and look at significance. So significance from a table. A test of the null hypothesis as mu equals 0 against the alternative hypothesis as mu greater than 0 has a test statistic z equal to 1.65. Is the test statistically significant at the 5% level? That's alpha equals 0.05. And is it statistically significant at the 1% level? Okay, so we are looking at a p-value here. We're actually looking at z-score itself. So one way, well, what p-value is the probability that you see a z-score more extreme than the z-score that you have. And you can look at the critical z-scores, or you can look at p-values, right? So if you have a critical z, which is your cutoff, then this would be your critical region. And you're trying to see, is a z-score of 1.65 in this critical region or not? If it's not, then it's not statistically significant. So we're going to find z-stars. So we want a z-star for the 5% level and a z-star for the 1% level so that we can determine if z 1.65 is greater than either of these values. If it is, then we have significance at that level. So we actually need table C for this. So if we click to get our table C here, then what we're looking at is the very bottom of the table. You've got that Z-star row that we've been using for confidence intervals, but now we're looking below that at the one-sided P and on the next one, the two-sided P. This is one-sided because we've got an alternative hypothesis that has a direction. We think that mu is greater than mu naught, for example. So our 5% level let's see. Oh, I don't know if you can see it because there's like a picture blocking on my screen. But right here we've got a Z-star of 1.645. And below it, we've got listed a 0.05. And then if you go down 1, 2, 3 more columns, we've got a Z-star of 2.326 for the alpha equals 0.01. Okay, so we have then a 1.645 and a 2.326. The 1.645 is less than the 1.65. Our Z-score is in the critical region when the cutoff is 5%. So you have 5% area to the right of this critical Z-score, but our Z-score is in the critical region. So this is significant at the 5% level. Okay. Now, and we could say Z is more extreme than Z-star. Okay. Now, the 2.326, however, we have a critical region that's like just over here. And our value of 1.65 is not in that yellow critical region, right? So this time around, we are not significant at the alpha equals 1% level. So not significant at the 1% level, which means we have some evidence, we even have strong evidence that we would reject the null hypothesis, especially if we were using the 5%. But if the customer didn't want to make changes until the 1% level, then this would not be significant enough information. Okay, so let's check with the book. Okay, so my thing's blocking it. Oh, there we go. I left the page. Okay, so using table C, we've got the same Z-scores, 1.645 and 2.326. We are significant at the 5% level. We are not significant at the 1% level. Okay, in this one, we're going to look at similar but two-sided. So here we have number 17, a test of the null hypothesis, which is mu equals 0 against the alternative hypothesis, which is mu is not equal to 0. That test has a test statistic, same thing, 1.65. Is this significant at the 5% level and or the 1% level, just like we saw before? The difference this time is we're dealing with the two-tail, right? So the not equal means two-tail because we don't really know if it's more or less than the old mu. We just don't think it's the old mu. Okay, so we're going to go to table C. We are going to look at the bottom. And this time we're going to look for the two-sided P. We need the 5%, which is here, and the 0.1, which is here. Again, I've got a camera picture over. Maybe if I shut my camera off, you can see it. Okay, that might work. Okay, so here we've got the 5% level. Here we've got the 1% level. So not to confuse you, but to go back, just in case you couldn't see it on the last example, this is what the one-sided look like. On one-sided P, which for us is alpha, we are looking for the 5%, and we found the z-score 1.645, and the 1%, we found the z-score 2.326. So now on our new problem, we have two-sided and our alpha equals 5% and 1%. So this time we're finding a z-score of 1.96 when alpha equals 5. And we're finding a z-star of 2.576 when alpha equals 0.01. These ones will match more with what you have been learning because this form fits our confidence interval conversation. So this one feels more like the values we're used to seeing. But sometimes you're doing a one-sided test, so you have to use the other row. Okay, so we've got our critical z's. This time, our z of 1.65, that's less than both the 1.96 and the 2.576. So no, not significant. At either level. We've got our picture, our original cutoff of 196, and our z-score this time is not in the critical region. And so when we pick an even more extreme cutoff, like the 2.576, we are still not in that critical region. So if you fail to be significant at the 5% level, you will also fail to be significant at the 1% level. So we have not significant at either level. Let's check what the book says. The book gives us a Z of 1.96 for the alpha 5, a Z of 2.576 for alpha 1. If Z is not significant at a particular alpha, it will also not be significant at a smaller alpha. We made that observation as well. And they said, just like we said, that it's not significant at either of these levels. So check, check. Okay, so now we're going to do a couple of multiple choice questions. We have so one thing is on this slide, I have the 3 different tests. The book uses the last 2 a lot, but the easiest one's the first one because that's going to be whatever the book tells you. This area will be what the book tells you. This area will be 1 minus what the book tells you. And if you use this as 1 minus A, this is also 1 minus A. And we have a p-value of 2 times 1 minus A. A being the value we get from the book, which tells us the area to the left of the positive z-score here. Okay, so you can use software to carry out a test of significance. The program tells you that the p-value is 0.052. You conclude that the probability computed, assuming that H naught is true, so definitely not the last one, because we always assume H naught is true. And then we have the second half. So assuming H naught is true, p-value is the probability, the test statistic taking a value as extreme or more extreme than the actual observed is 0.052. Or B is less extreme. So that's our choices that we're down to now. More extreme or less extreme. And it's definitely more extreme because if we're in the critical region, then we are more extreme. If we are in the unshaded region, that's common. Anything in there that seems unusual is just due to chance. But anything in the critical region, that's not due to chance. That's unusual. And that's worth investigating or making decisions about. That's statistically significant. So it's the first choice because we assume the null hypothesis is true, and p-value is the probability that we will take on values more extreme than the one observed. Okay, so the book says A, true. This is the definition of the p-value. So we're looking for true and the test statistic taking on a value as extreme or more extreme than the actual observed value. The p-value tells us the probability of that is 0.052. That's an important phrase to remember. That's why I included it here on the slides. You want to remember the definition of p-value. In 23 and 24, we're looking at this mouse maze. Experiments on learning in animals sometimes measures how long it takes mice to find their way through a maze. The mean time is 18 seconds for one particular maze. A researcher thinks that a loud noise will cause the mice to complete the maze faster. She measures how long each of the 10 mice takes with the noise as stimulus. The sample mean is x bar equal to 16.5 seconds. The null hypothesis for the test of significance is, now the null hypothesis is such that mu equals mu naught, not x bar. So mu naught is 18. And we have option A. The alternative hypothesis for the test in 23 is actually the mu being less than, because they said that the researcher thinks that the loud noise will cause the mice to complete the maze faster. So if you are faster, you are taking less time to complete something. So this one represents our mice being faster. So mu less than mu naught. Okay. So our less than, which we don't get a lot of examples of, we at least have one here. They didn't have us calculate the p-value because we could though, if we wanted to on our own, right? So we could calculate a z-score and then find that value in table A. Let's see. Just curious, right? So z equals x bar minus mu naught. Oh, maybe we don't have n. Oh, we do, 10 mice. Okay, so we definitely can compute this. They didn't give us sigma. Oh well, it was a fun idea. Okay, so they didn't give us sigma, so we actually can't compute the z-score or the p-value right now. But this is at least the wording for an example with a less than in our alternative hypothesis. So let's take a look at what the book says. A, mu equals 18, and B, mu is less than 18. So the null hypothesis states that mu takes on the default value, 18 seconds, right? There's no difference. There's nothing to see here. Everything's the same as it always was, versus what the researchers think. So you always look for what the researchers think is going on and then articulates that into an alternative hypothesis. So here they say the researcher believes that loud noises will make the rats complete the maze faster, therefore decreasing the completion time. So the alternative is one-sided. So that's one thing. We do have to start acknowledging when we have one-sided tests and when we have two-sided. I try to do that acknowledgement by including the visual from our p-value display in the summary so that we can constantly see those three situations that we have for our alternative hypothesis. Okay, now we're going to actually do a couple of the tests, like to completion. So we've been stating what the tests are. We've been finding the z-score, even finding the p-values. We compared z-scores once to do the test, but now we're going to do the p-value test, like in its full glory. Twice. Okay, so number 28, student study times. In exercise 16.19, which we've included, this exercise describes a class survey in which students claimed to study an average of 13.7 hours in a typical week. Regard these students as an SRS from the population of all undergraduate students at the university. Does the study give good evidence that the students claim to study more than 13 hours per week on average? To the students' claim, there's a bunch of typos in this one. Okay, so A, they want us to state the null and alternative hypothesis. We need things for that, like mu naught, right? So we actually have to look at the problem 16.19. Oh, whoops, I did a reveal. Okay, so in 16.19, they give us the values that we're looking for. So we have an n equals 463, x bar equals 13.7, same as they told us in our problem. Sigma equals 7.4. And let's see, we need mu naught, no? Mu naught is 13. So they're saying here, right, that the students claim, so that's the alternative, the students claim is that they're studying more than 13 hours. So that's that is our anchor here, right? So we get a more than on this one. The null is always that nothing has changed, right? Everything's the same. It actually is 13 hours that you study and not more, right? It's exactly 13 on average, as a matter of fact, right? Okay, so that's A, just stating our hypotheses. When you state your hypotheses, you also make the acknowledgement that this is a one-sided test. That way you can use the proper image and p-value. So I like the summary on this chapter, and I like to keep that thing nearby when I do p-value tests so that I do the right thing. Okay, so step A, complete. Step B, we have what is the value of the test statistic Z? And it's up in the corner, but I think the camera's covering it, so I'm not sure if you can see it, but I have been writing it every time nonetheless. So we're going to find our Z score, right? So I'm going to do Z equals X bar minus mu naught divide by the standard deviation, sigma over root n. So we have 13.7, take away 13, divided by 7.4, which is itself divided by the square root of 463. So that's your denominator. And then that gives us the value of 2.035, which I put so we knew to round z to the 2.04. So z is 2.04. And we're going to use that z-score to find information about the p-value, right? Okay, so what's the p-value of the test now is what they're asking us for letter B, no, for letter C. So the p-value, and then they should have just split this up, right? Find the p-value and then make your decision, but they put it in one question. So we're going to find the p-value and then we're going to make our decision, right? So using the table A, you go find your p-value, you go find your z-score, the 2.0, and then at the top here ending in a 4, and you find that the area that they've given you is here, right? The book tells us the area to the right, so we need to find 1 minus that value, right? 1 minus the 0.9793. That is the value of 0.207. Okay. And now they didn't give us an alpha. So you're like, how do I decide if this is big or small if I don't have an alpha, right? When they don't give you an alpha, your default is 5%, right? Like we started off talking about outliers and rare things and being unusual and what does it mean to be unusual, right? And generally the 5% is the cutoff. We even use that in terms of the 95% confidence interval being the general interval, right? And so this 5% then marks usual from unusual. And so if we're not given an alpha, you can use like alpha equals 5% as something to compare your p-value to. Our p-value is smaller than that, right? We've got a p-value giving us a 2.07%. So we've got 2%, which is smaller than 5%. So it does not appear that our result is due to chance, right? It does seem significant. So we're going to reject the null hypothesis and we're going to accept what the students are saying, right? We believe them now. They do appear to be studying more than 13 hours a week, right? So can you conclude that the students do claim to study more? I hate the way this one's worded. What do you mean? We're not proving they claimed something, right? You can claim something. We're proving they studied, right? So can you conclude that the students do study more than? See what I mean? Like there's some wording issues on this one. Do you study more than 13 hours per week on average? And we're saying yes, right? So let's see how I worded it. So I said for part C, I said P is small. That's like my first statement, right? P is small. So it follows that there is a strong, well, I didn't say a, there is strong evidence that the students do study more than 13 hours per week on average. So we got a p-value. That was part of it, right? So maybe we should include that in our C statement as well, right? So p-value equals 0.0207. So it's good to be explicit, right? We've got our z-score explicitly labeled. We've got our C p-value explicitly labeled, right? Here's our hypotheses test from A, and then our conclusion as part of C is down here. Okay, let's take a look at how the book worded it. So the book says they got the same, let's see, they got the same tests that we wrote. The only thing I didn't write that they have here is units, which that's important, right? And it might be worth points on the test. So maybe we should be writing the units the way the book is doing it. So look at the answer for A. They're saying 13 hours per week. So maybe we should be putting like hours per week on our stuff too, right? Because usually if the coordinator does that on the test, it's worth a point or so, right? Okay, let's see. And just as an in general thing, we are trying to pretend to talk to our clients, right? And they want us to understand the units of their situation. So it's good to practice it. Okay, so let's see. And then they have the same z-score as us, check, check, and the same p-value as us. Oh yeah, I forgot. I meant to write it well. Okay, so let me write it well. So on my paper, right, I wrote p-value is equal to the probability that a z-score is greater than the observed, and that is 0.0207. Okay, and then that is us using the p-value rule from the book. Okay, so now I think it is most complete. Okay, last problem. Number 30. We've got hotel managers' personalities. Successful hotel managers must have personality characteristics traditionally stereotyped as feminine, such as compassionate, as well as those traditionally stereotyped as masculine, such as forceful. The BIM sex role inventory, the BSRI, is a personality test that gives separate ratings for female and male stereotypes, both on a scale of 1 to 7. Although the BSRI was developed at a time when these stereotypes were more pronounced, it is still widely used to assess personality types. Unfortunately, the ratings are often referred to as femininity and masculinity scores. A sample of 148 male general managers of 3-star and 4-star hotels had mean BSRI femininity score of an average of 5.29. The mean score for the general male population is 5.19. Do hotel managers, on the average, differ statistically in femininity score from men in general, assume that the standard deviation of scores in the population of all male hotel managers is the same as the sigma equals 0.78 for the adult male population. We're going to state the null and alternative hypothesis for the parameter mu. We need our mu naught for sure. So mu naught is the population mean. Our X bar is 5.29. Our sigma was given to us at 0.78. And we have 148 individuals. So N equals 148. We need to write our hypotheses. So the null hypothesis is always mu is equal to mu naught, and the alternative is mu. Here, let's see, what do they want to know? So find the question. Oh, it's in the second paragraph thing. Do hotel managers, on average, differ? So just not equal to the score for men in general. Okay, so our null hypothesis then is mu equals 5.19, right? Nothing's changed, nothing's different. They're exactly the same. There's nothing to see here. Move along, right? So the null hypothesis is always that there's no difference, right? There's no difference. They're the same. Our alternative is the one that we have to figure out. Here, researchers are saying, no, maybe they're different, right? Maybe they're not saying how, they're not saying if they're more feminine or more masculine in terms of this survey. They're saying different, right? So you probably need to be super forceful to be a hotel manager, dealing with drunk party people and all of that kind of chaos that happens in a hotel, right? So they aren't saying which way it's different. They're just saying maybe those people are special, more special than the average. Okay, so we have our answer for A right here. And secondly, for B, they're asking for the z-test statistic, which we have the formula for here. So we're going to just use it. So we have z equals x bar minus mu naught divided by sigma itself divided by root n. So we have 5.29, take away 5.19, and we're dividing by the ratio of 0.78 divided by root 148. This gives me a value of 1.559, which means I need to round my z-score up to the 1.56. So there's my z-score. And we need table A. So, well, one thing we didn't acknowledge yet was that this is a two-tail, right? So at the end of stating our hypotheses, usually part of what you're saying in the alternative is if there's a direction, it's a one tail. If there's no direction, just differ, it's a two tail. So we're dealing with this situation here where we have the two tail. right? And now we need our table. So here's our 1.5 ending in a 6. And you can see here the table information given to you, which is the value on the left. That's value A, right? They tell us that that is 9406. So that's from the table there. And the first step is to find 1 minus A, to find this shaded area to the right. 1 minus A, 1 minus 0.9406 is the value 0.0594. You can't see it very well, but we'll rewrite it over here. Okay, so we're working on part C officially. We're looking for the p-value, right? P-value on a two-tail is 2 times the probability that z will be more extreme than our z-score of 1.56. And we know that to be 2 times 0.05, 0.05 equals, I thought I'd be able to read it and I can't, 9, 4. Okay. That is 1188. Oh, that's 2 zeros though, isn't it? 1188. Okay, so that's our p-value. And we used this p-value portion of the table from the summary list to help us find the correct p-value. When you have a two-tail, you need both of the blue zones, right? You need both regions there. So that's why we're doubling it, because more extreme than that z-score means on either side, the positive side of z-scores or the negative side of z-scores, because we didn't pretend to know if we were saying how these people differ, right? We weren't saying that at all. Okay, so a 0.11, that is not small. So that's what I said. So for to continue C, I said P is not small. It's not huge either, but it's not small in that it's not less than 5%. But you can have a 90% confidence level, right? So this is like a 12% alpha or an 88% confidence level. So it's not terrible either, right? So it's like weak evidence, maybe. So I've got there is weak evidence that hotel managers have a different mean than the general male population. And I don't know if I can write that far on my screen because my toolbar is down there. I'm just gonna have to write it over here. Sorry about that. Oh, that's why I'm not an architect. Okay, so let's take a look at what the book says, and then you can be on your way. Okay, so let's read the last one first so I can erase this. So, oh, I can't read it. So we'll just maybe recall this if I have to. So, all right, so let's read theirs. They have mu equal to 5.19 for H naught. We had that as well. They have mu not equal to 5.19 for the alternative. Another typo. They accidentally put H naught twice, but that's our alternative. And it's two-sided because we just are looking for a difference, right? So check, check, check on number A. B, they got the 1.56 just like we did. So check, check again. And then their p-value matches our p-value. But really, we want to know the way they worded it. So there is only weak evidence that hotel managers have a different meaning. What about that? There's only weak evidence. I'm getting echo here. Okay. Really know. Okay, no echo. All right, so there's only weak evidence that hotel managers have a different mean femininity score than the general male population, particularly when the large sample n equals 148 is taken into account. We suspect that hotel managers don't differ much from males in general in this respect. Okay, so I had to shut the tablet off because there's too much interference. Okay, so that is all that I wanted to show you today for chapter 17. Please let me know if you have any questions. Feel free to send me an email. And otherwise, we will be reviewing for the test next.